Hello and good afternoon. Welcome to, I believe, third lecture of SC350. Today we'll continue the lecture on OS concepts. If there are any questions from the previous lectures, please feel free to ask them in the Q&A. Okay. So we talked about threads, and we started talking about the second concept, which is address space. We introduced the two main address spaces, physical address space and virtual address space. We mentioned that the physical address space is basically the range of addresses that you can use to access your physical memory, and the values that are stored in your physical memory. A virtual address space, on the other hand, is the addresses and the values stored in those addresses that are accessible to a process, regardless of the physical memory. And we mentioned that in a 64-bit system, a process could potentially address anything from 0 to 64 bytes. In a 32-bit system, a process can access anything from 0 to 32. Now, the same virtual address, so process 1, let's say, addresses virtual memory of 0, and then process 2 also wants to access virtual memory 0 or virtual address 0. So these two virtual addresses are separate. One is for process 1, one is for process 2. Now, these two virtual addresses potentially are mapped to different physical addresses in the physical memory. Maybe we map virtual address 0 of process 1 to address 10, and virtual address 0 of process 2 to address 20, right? So this is the job of the operating system, to do this mapping from each process's virtual address space to physical address space. Now let's look at how a typical C program is organized in terms of its virtual address space. So I have here a program. The code of this program, the binary code, goes at the bottom of the virtual address space. So this is address 0 all the way to address FFFFF, depending on how many bits your system has. So the number of these Fs and zeros depends on the size of virtual address space. Now the bottom part basically has the code, the binary code. Now all the global variables that are initialized, like this one, why we initialize it to 15, they go on top of the binary code. Anything that is not initialized goes on top of the initialized ones. Now, the environment variables and the inputs to the main, they go, oh, sorry, before going there, anything that we dynamically allocate, any memory that we dynamically allocate, like here, value is equal int star malloc size of int times 5. These guys go to the heap. the command line arguments and the environment variables, they go on top. Then we have the stack. So anything that any variable that you define inside your functions, they go on the stack. And then any library that you might use gets virtual addresses that are mapped between your stack and your heap. So the heap grows towards the higher addresses, whereas the stack grows towards lower addresses. Now, if you want to, for example, grow the stack, you usually do minus stack pointer. You know, this is how we usually write to the stack. Let's say I want to write to stack value 2. This is how I write. I decrease the stack pointer. That's how the stack grows, by decreasing it. And then I put something in it. Whereas heap, you know, grows this way. I got a question here. It says uninitialized or initialized data is like global variables. Yes. So these are your global variables. If they are initialized, they go first. If they're not initialized, they go second. So one question you might ask is, why do we put shared libraries between a stack and heap? The reason is this area here that is not initially allocated is where we do everything that needs to be done dynamically. Now, we have two options when it comes to libraries. We can, you know, put the libraries, we can give the libraries virtual address, all the libraries that you use, but that is wasteful. So usually these libraries are really big, right? And then you might have so many of them. But the fact of the matter is that sometimes you actually don't use a library. You might actually have a code here like this. If, let's say value, let's say if x equals 2, then printf. So now this printf, we may or may not really use it depending on this condition. Now, if I come and you know, map a stdio to my address space, it's wasteful because there is a chance that I actually don't need that library. So this is called dynamic linkage, and I talk about it when we talk about virtual addresses in the second half of the course. So we talk about this particular thing in a little bit more details, but it's called dynamic linkage. So we dynamically link whatever we need. So when you see these libraries on top, they don't necessarily get mapped to your virtual address space. They only get mapped to your virtual address space if your program uses functions from that library. Okay, now let's talk about a stack and how it grows. So we're going to talk about the stack of execution and how it grows. So we usually want at least two things on the stack. So let's just take a step back. Stacks are used for function calls. That's their primary use. Now, we use them for mainly two things. First, as I mentioned, the variables that our functions use, they go on the stack. The second important thing that usually goes on the stack is the return address. Where should we return once we're done with this function? So these are the two primary things that we save on a stack. Now, here on the left, I have a program. So line A0 to A4, this is a function. This is function B, the definition of it, and then this is function C. So it's kind of like a nested function call. A calls B, B calls C, and then C calls A. So that's the function definition. Let's assume that PC is here. So we want to execute this line. Let's say we want to execute A1. So this is a function call. The variable to this function is 1. So we basically push that to the stack. We say this is the variable. And now, where do we want to return? So we want PC to be pointing to this ext once we're done executing this function. So as a result, we also push this ext on the stack. So right now, this is the beginning. My stack looks like this. There's temp and there's a return address for me to return. Now, okay, let's continue see how this program executes. Next, we're going to jump to A, right? So now this time PC is going to look like this. So now PC is pointing to A1. Now let's execute this. This says if TMP is less than 2, well, we look at the stack. That's where our variables are. And we see that TMP is equal to 1. So 1 is less than 2. Therefore, we're going to call B. So we're going to go to this one. Now, here is another function call. What do? We push variables and return values. There's no variable in B. If you look at B, it has no variable. So we're not going to push anything for B. But we're going to push the return address. The return address, once we're done with B, we want to go to A3. So that's what we're going to push. We're going to say return address is A3. That's where I want to go once I'm done. Now, PC now points to B1. So we want to execute C. Now, this is another function call. If you look at C, C also doesn't have any variables. So again, we don't need to push anything in terms of variables, but we need to push the return address. In this case, B2. So we push B2. Now we're inside C, and C is going to call A. Now another function call, so we have to push this stuff on the stack. Well, A does have a variable, which is its argument A, which is temp. Now temp is going to be 2. This is what we're pushing. And where do we want to return? We want to return to C2. So we're going to push these two. We're going to push temp equals 2, and return is C2. Okay, now PC now this time points to A1. We look at temp. Temp is equal to 2, so it's not less than 2. So we're going to print. So we're going to execute this line. We're going to print temp. So this basically the emulation of the terminal. So we printed 2. Now PC advances to A4, and A4 is a return. So A4 is the end of A, so it has to return. Where do we return? Well, this is where the stack comes handy. We're going to look at the top of the stack and see where to return. And we see that the return value here is C2. So after this line, we're going to jump to C2. So this is a jump. PC is going to jump from here, from A2 to C2. And the way we know it is because we have it on the stack. Okay, so we jump to C2. Now, what is C2? C2 is also a return. It's end of function C, so we have to return. Now, again, we have to look at the stack to see where should we return. And we see that the return value here is B2. Okay, so we're going to return to B2. Again, B2 is a return, right? So again, we're going to look at the stack to see where we should return. Well, the return value is A3, so we're going to go to A3. Now, here at A3, now PC is here, so we will execute this printf. So I have already executed it. So we print 1. We're going to print temp. So we look at the stack again. We see temp is 1. So we return TMP. And now we're at A4. OK, so A4 is now a return. So we again look at the stack. What do we have on the stack? We have our return address, which is ext. So we go to ext. So hopefully this example kind of shows how stack grows and shrinks as we execute our programs. If you have a recursive function, you might just add, and at some point you might have a Stack Overflow because your stack is just growing more than the space that is allocated to your stack, and then you get a Stack Overflow. Okay, so we're done with the 2 concepts. The third concept, which I sort of promised 100 times in the previous lecture to talk about it, is the concept of process. So this is the third operating system concept that we're going to talk about. What is a process? In very, very high... OK, so I got some questions. I'm assuming they're about the virtual address space, so I'm going to answer them before jumping to processes. So the first question says, is this virtual address space layout? Is this virtual address space layout mandated by the OS, or is it just the C linkers convention? So this basically is a convention. It's not mandated. Oh, I'm not going to go up there, but yeah, it is a convention by the C linker. Operating systems do not. Operating systems provide system libraries, like, for instance, C linker or any other kind of linker to facilitate memory allocation, right? But then that would be the convention in that language, how to use that virtual address space. So to clarify, and another thing, yeah, that's pretty much it. So to clarify, what processes specifically happen in the heap? Is it just data allocation? Yeah, so the heap is basically your dynamic memory. So all the mallocs, whenever you new an object, so these are dynamic. When you code, the compiler doesn't know if this is going to happen or not, what is the size of this. All the static variables, they have their own place. They're static. So at compile time, we know how long and how large each data structure is. So we can allocate memory to them. But the dynamic allocations happen online, like at runtime. So that's where they go in your heap. So you request data. Sorry, you request memory space using malloc, using new, and then the operating system gives it to you. So that's the usage for heap. And by the way, that's what you're going to implement in lab 1, right? So let me go back. In lab 1, it's 2. So in lab 1, you're implementing the malloc function. So you're going to basically manage the memory at runtime. So if your program says give me 10 bytes or 20 bytes, your program, the operating system, which manages memory, allocates that and returns a pointer to the program and says, here is a pointer. Now you have that allocation, you can use it. In your project and in EC350's project, we don't have a concept of virtual address. So we're just using physical address. And that's usually true for most of embedded and real-time systems. So they don't use virtual address, and they allow processes to just directly access physical memory using physical addresses. The reason for that is, as unfortunately not in SC350, but the reason for that is virtual. This mapping from virtual address space to physical address space has overhead, right? Because your process talks in the language of virtual address, and that has to be translated to physical address to basically go and find the data in physical memory. And this process of translating virtual to physical memory addresses is time consuming. And it's sometimes non-deterministic, how long it takes for this translation to happen. So we actually, if you look at the website, there is this address translation section of the course in the second half that will talk about this translation. But as you will see later on, sometimes we can do it very fast, and sometimes it takes time. And this is bad for real-time systems. In real-time systems, you actually want guarantees on how long each thing take. So most of real-time systems actually forego having virtual address space. So the benefit of having virtual address space is isolation, because if each process has its own virtual address space, then they cannot access somebody else's virtual address space. They just have their own virtual address space from 0 to 264 or 2 to 32. And somebody else has their own 0 to 32. And then the operating system manages that. So with virtual address, we can get isolation, but the cost is performance, as we will see. If you forego virtual address space and allow processes to just access physical memory with physical addresses, then you get performance because you don't need to translate, but it's less secure, obviously. Operating system has less control over managing the accesses. For instance, in your labs, a user process can go and mess up the operating system code, and this will happen when you're coding. Sometimes your user program Stack Overflow messes up your kernel code because there is no protection, right? But then one of the reasons that some embedded systems take this route is because the programmer and the operating system designer is the same person usually. Like if you're sending a satellite and you're writing an operating system for your satellite, you're also probably the one that is going to write applications for this satellite. So you can make sure that you're adhering to the protocol and not messing things up. Anyhow, so enough of that. So another question is, so when the memory is freed, is that moving the pointer back to where it originally was? How do we preserve the old pointer when a piece of memory is freed? So I'm doing a bunch of stuff now. So this is your, let's say this is your, this is the beginning of heap. Let's say address X. So this is the beginning of the heap, and then let's say heap is growing this way. Now, let's say you ask for 10 bytes. So somebody says malloc 10, give me 10 bytes. So your operating system will just, allocate 10 bytes, blah, 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 blah. Your operating system probably needs some metadata as well to say, let's say, this is where like in lab 1, this is the overhead. So let's say here we say the next 10 bytes are allocated. So this is kind of like a metadata. And then we say the pointer to free memory is this. So now this points to free memory, and I have allocated these 10 bytes to my, program, and then I return this address here. I say this is the beginning of your memory. Now, so let's say next time I do a malloc of, okay, let's actually do it better. Yeah, that was good, but I messed it up. Yep, please discard. How do I insert a new slide? Okay. So okay, let's say let me do it bigger. Okay, so let's say this is the beginning of heap, address X, right? And let's say everything here is free. Now somebody says p star void star p equals malloc 10. So what's going to happen is that the operating system puts some metadata here. Give me a sec. Which potentially says, okay, the next 10 bytes are allocated, and the pointer to free space is something, right? And then you allocate the 10 bytes. So now this whole area is used, and and this pointer points to this one. Now let's say I go and then later on I do another one, void star P1 or P2. Oh, and then P1, basically P1 will point to the beginning of this memory. Now P2 becomes malloc, let's say 20. Okay, so now your memory management starts from X. It says, oh, the next 10 bytes are allocated. The pointer to the free space is here, so it comes here. It says, now I want to allocate 20 bytes. It says the next 20 bytes are allocated, and the pointer to free space now is here. Let's say we allocate 20 bytes, and now the pointer becomes here, right? So now this area is also allocated. Then later on, you come and say delete or dealloc. Let's say we say dealloc P1. So what happens is the operating system comes and says, oh, okay, so this area here is no longer needed. Please, for God's sake. So the operating system says, okay, I'm deallocating this area. So this area becomes free again. This area becomes free. So now this area is again free, and this is free. So next time, if you want to do void again, let's say you do P3 equals malloc 30, right? What happens is that, and by the way, here I'm sort of implementing a first fit. There are other implementation. I don't exactly remember what we are asking you in lab 1 to implement. There is body, there is this one that I'm saying first fit. So the way you find a space to allocate is different depending on what allocation mechanism you're allocating. But anyhow, let's say we're doing the simplest one, which is first fit, which is basically when I say, okay, now allocate 30. Now the operating system comes from X, looks at this, it says, oh, this is free. And we probably have some metadata again here saying that there is 10 bytes free here. And we probably want to then have a pointer to another free space, which is here. But anyhow, this is a data structure that your operating system will have to have. Now, the operating system says, okay, I have 10 bytes here that are free, but this guy is wanting me to allocate 30. So I can't allocate it from here. So it jumps here and says, oh, here I have it. So then it allocates, it puts some metadata here again. It says the next 30 bytes are allocated, and the pointer to the next one is probably here. So it allocates 30 bytes. So this 30 byte now gets allocated, and a free space is here. So at any given time, the operating system knows which portions are free and which portions are allocated. Now, if you over time, after some time passes, let's say this is your memory now horizontally, you might actually have some fragmentation. So this area is allocated, then there is some free area here that somebody deallocated, and then some area is allocated, and then there is another free space here, and then some area is allocated here, and so on and so forth, right? So after a while, this is how your heap will look like. Some areas are allocated, some areas are free, and then the operating system has a data structure to track all of this. It has to know which areas are free, which areas are allocated, and there shouldn't be any memory leakage, meaning that if you deallocate memory, let's say I allocate 10 and I deallocate both of them, I should go back to what I had initially. So your algorithm should make sure that the memory is not leaking, meaning that the memory is not shrinking as I do these allocations and deallocations. Okay, let me answer some of the other questions that are posted. Where does the translation of physical to virtual memory actually happen then? Usually it happens in hardware. This is one of the areas that operating system relies on hardware support to do the translation. If you're interested now, you can look at page tables. But we're going to cover this. So the second half of the course, we'll talk about address translation. So don't worry. I mean, if you're really not believing me, go to the course website. Where is Chrome? So this is the course webs. Oh, this is ECE. This is SE. Here. Look here, address translation. So we're going to talk about address translation in the second half of the course. So after we come back from, God damn it. After we come back from the reading week, we'll talk about address translation. So we'll come back to this concept of address translation later on. And as you can see, it takes some time to actually cover everything. Okay, going back. Okay. Another question. So when the memory is freed, is that moving the pointer back to where it was? Okay, does this mean your heap can end up with a bunch of holes? Yes, as I explained, as I just showed you. Your heap could become fragmented. How does the OS know how much free space a chunk has? That's pretty much what, so operating system is in charge of the memory, right? So when somebody is asking you, give me 10 bytes, you probably want to write this down somewhere that I gave the next 10 bytes to this guy so that you don't give it to somebody else. And when they come and say, okay, I don't need it anymore, free this space, you want to say, okay, this 10 bytes are free. So that's basically the metadata that I talked about. So the operating system basically saves these metadata. Now, when we talk about utilization and when we talk about overhead, we're talking about these metadata. So this metadata that the operating system puts here for tracking is basically the overhead, because this metadata is not accessible to the user program. The user program gets this 10 bytes that they asked, or this 20 bytes that they asked, or this 30 bytes that they asked. The operating system keeps these metadata hidden from the user program. User program should not touch these, right? And this is the space that the operating system is kind of keeping for itself for tracking, and that's the overhead, right? So this is where we basically keep track of what is free, what is not free, pointers to the free spaces, pointers to the whatever, however you're implementing your memory allocation mechanism. Okay. Now, hopefully I answered the questions about address space. Now let's talk about processes. Okay, what is a process? First T. A process is a program in execution. That's pretty much it. Now, if you can have two instances of the same program. For instance, in this figure that you can see, I have Microsoft Word. I have opened two windows. Each one of them is one process. So each instance of the program is a process. It's kind of like classes and objects in C++. So a class is similar to a program. And then when you instantiate from it, you get an object. That would be the process that is running, right? So for each process, the operating system needs to store some information, some metadata, as always. What are the things that, so first of all, where? So we write operating systems track of processes in memory. So they create these process control blocks, PCBs, to keep track of processes and have some information about processes. What do they usually keep track of? What is the status of my process? Oh, maybe I start with this one. It's kind of like a PID, the process unique identifier. What is the state of the process? Is this process blocked? Is this process finished? Is this process running? What is the state of this process? And then the priority. What is the priority of this process? Is it a high priority, low priority, whatever? What is the program counter? What are the registers? What are the memory pointers for this process? What's the I/O status of this process? Let's say if you open a file, you get a file descriptor. So what are the files that this process has opened or is working with or is writing to or is reading from? And some accounting information. Okay, so every time we are not running a process. If the process is not running right now, for whatever reason, maybe it's blocked on I/O, maybe this process wanted to access I/O and it got blocked. Whenever we're not running a process, we basically want to store the context of the process in the PCB. So we want to say, where was the PC when we were running this process? What were the registers status when we were running this process last time? We don't need to keep track of these information when we are running the process, because they're just keep changing. Like PCs keep changing as we execute our process. So there's no point in keeping track of it. So we only need to keep track of PC when we stop running it. So we want to know where should we come back next time we want to run this process. The same with the registers. So registers are going to change as we run the process. So at some point, we want to, put this process aside and do some other processes. Then we want to take a copy of the registers and save them in the PCB. Okay, so let's look at this PCB and see what happens to it during the life cycle of the process. So when you create a process, the operating system creates a PCB for that process, obviously. And then the operating system initializes the data in this new PCB, like gives it a process ID, sets initial states, sets initial values, sets the PC, for example, to the first instruction in this process to be executed. And then sets up a bunch of other things, like what are the memory regions that this process can access. As we will see later on, sets up the page tables for this process to indicate the physical memory address, virtual to physical memory address translation for this process, and all of that. So that happens when the operating system initializes the PCB. So this PCB could have a pointer to the page table for this process, which I haven't mentioned. So one thing to note is that these are kind of like these are usually included, but it could have much more. For example, you could have, how long this process has been running. What is the user of this process? Which user created this process? What process created this process? As we will talk about it, like who is the parent of this process? Again, I'll talk about that later. So it has some more stuff in PCB. Now, once the process is created, this PCB gets added to the list of PCBs that the operating system has. So operating system usually has a list of all the PCBs that it has created, and they're active or they're swapped to the disk, which we will talk about. So once it's created, it will be added to the list of PCBs. Now, at some point, the process exits and terminates. By the way, I actually looked it up. So if one thread calls exit, all threads die. So it doesn't matter if it was the main thread or the children, whoever calls exit, the entire process exits. So if you want to just exit from a particular thread without terminating the entire process, you call pthread exit. So with this one, only this thread exits, and the rest of the system, the rest of the threads will continue. Okay, so coming back, if a process terminates, if a process exits, then the operating system removes its PCB from its list of active processes. And then probably frees the memory that it has allocated to that PCB. If the PCB, is so, for instance, in some real-time systems, you might have, at the beginning of so you might have a certain number of PCBs that you will have in the entire execution of your operating system. So you might actually want to allocate statically in your in the operating system image, which is, by the way, the case in your labs. So the PCBs, although in your case they're called TCB, task control block, they are statically allocated, but it could also be dynamically allocated, right? So the operating system also frees up the memory that it has used for the PCB. I got a question. I will answer that question once I'm done with PCBs and stuff. So if I haven't answered the question, I'll come back to it. Okay, so during the execution of your process, as I mentioned, we're gonna, let's say we have only one CPU. This CPU is going to run a process and then context switch to another process. Let's go back to the example that I had. Let's say I have a machine with one CPU and I have opened two Microsoft Windows programs, and I'm editing two different files, right? So once P0 is running, the other one is idle. The other one is not running, right? Let's again assume that there is one CPU here. At some point, for some reason, we pause the execution of process 0, and we want to context switch to process 1. At this point, so it could be an interrupt, it could be a system call, it could be an exception like a divide by 0, or a segmentation fault or whatever. So we'll talk about that later. So for some reason, we're going to pause here. What do? We save the state into PCB. So here, mostly we're talking about PC, the program counter, the registers. If we want to keep track of, let's say, the time that this process has been running, we can say, from the last time that it started execution until now, it took like, let's say, 10 nanoseconds or whatever. So we keep track of those as well. So anyhow, we save whatever we want to save in the PCB. Then we do a bunch of other things, which we will see what they are in these lectures. I don't exactly know if we will have time today, maybe in the next lecture, but we do some other things. And then we go find the PCB of process 1. We look at the PC, the registers inside this PCB that we saved last time, and we load them to the registers in the processor. So we make PC in the processor point to where we saved in this PCB1. We load the registers to the processor, and we get ready. At some point, we execute a command, and we go to this process. We start executing it. Again, whenever we pause executing P1, again, we save the state into PCB of process 1. We grab PCB of process 0. We load its information on the CPU, and then we switch to process 0. So that's pretty much what happens. Now, let's talk about how processes are created. Okay, I think this is a good time to answer the question about PCB before I move on. So what data structure is most commonly used to store PCB? That's a good question. For the PCB itself, you probably can just get away with just a simple a struct, right? A simple C struct. You can store whatever you want to store. The part that is important how you manage is the list of PCB pointers. So if you have a bunch of PCB pointers, as I mentioned here, this list of PCBs that operating system has, this one is important, right? How you store these PCB pointers. Do you use a linked list? Do you use a binary tree? Do you use a red-black tree? So that there you have a lot of choices to make depending on what you want to achieve. And then, as we will see later on, we might have different PCB lists. So we might have a list of PCBs that are waiting for I/O. We might have a list of PCBs that are ready for execution. We might have a list of PCBs that are blocked. We might have a list of PCBs that are, waiting for NIC card or whatever. So we might have different lists of PCBs, and it's important then how we manage these lists depending on what we want to achieve. To understand a hierarchy, do threads belong to processes? Yes, I promised I will talk about that, and I will talk about it. Let me show you so that your hearts are at peace, and then I'll come back. I promise. I have a slides. I'll explain the relationship between threads and processes. It is here. A process has at least one thread, and it could have multiple threads. So a multi-threaded process has a bunch of threads. In the most common, in the past case, a process had one thread, right? And most of the things that right now I'm talking about a process with only one thread. When processes have multiple threads, I will come back to this slide, hopefully today, if I get a chance, to talk about the relationship between processes and threads. Okay, hopefully your heart is at peace. We'll talk about it, I promise. Publish. Okay, so you mentioned that PC plus register values are stored in the PCB during a context switch. I assume local variables of that process are left unchanged when context switching. Is that correct? So the local variables are in memory, right? So as long as you don't touch the memory of a process, then they're saved. So other processes hopefully cannot touch this process's memory because operating system is providing isolation. And hopefully the operating system is not going to go and change the memory of this process, this pool process. So in that case, it remains unchanged as long as it's in memory sitting and you don't lose power and stuff. So it's going to sit in memory, nobody's going to touch it. Okay, so in this context switching between processes, is this context switching between processes expensive? Having to save and load each, you bet it is, yes. Context switching between processes is very, very expensive. I have slides for that. Okay, you guys are just jumping too ahead of yourself. Okay, so why do both this TCB and PCB store register values? If a process is grouping of one or more threads, wouldn't its threads have this information? Never mind, looks like we'll cover it later. Thank you. Yes, we will. So as I said, right now, whatever you saw was for a process with one thread. So if you have a process with one thread, you probably don't want TCB. You don't need thread control block. You can store everything in your PCB. If you have multiple threads, then you will have multiple TCBs for each thread, and you store PC and registers for each thread separately, right? As you might imagine. Okay, I don't know how it relates, but will we ever talk about CPU hyperthreading? Yes, I have slides for that in OS concepts. Yes, we'll talk about it. And it is not related, actually. Hyperthreading is in hardware. We'll talk about it. Okay, let's continue. How do we create processes? There are different ways of creating processes. Usually, they get created at system boot up. When your operating system boots up, it starts creating processes. One of the examples is this login process. Once your system comes up, you see in the terminal login, and then you put username and password. That's a process that the operating system has created. We'll talk about process tree in a bit. In embedded systems, for example, the lab that you're doing, usually at the beginning of the system creation, we know how many processes we're going to have in total. So we can actually create PCBs for all processes that we will ever have. Let's say you have a satellite. So you better know how many and what are the processes that you want to run, right? So it's kind of like hard-coded. In general purpose operating systems, that's not the case, right? You might spawn different numbers of processes. So it's kind of like dynamic. Okay, the second way of creating processes is like by user requests. You go, you find the Firefox icon, you double click, you create a new process. So the user asks for a process to be created, and operating system says yes, sir. The third way, which we'll talk about, is one process spawns another process. And sort of this third one is kind of like, it also includes the first one, because in the first one, there is a process that takes care of your UI. And then when you double click, that UI process creates Firefox process. But anyhow, I just wanted to, separate them. But for instance, when you click on a link in your email, there's a link you click. So then your email application, let's say you have a Thunderbird, it spawns Firefox, for example, or Safari to look at the link. It spawns a web browser. Or when in command prompt you put ls or top, what is happening is that the terminal is a process. Then it creates another process, an ls process, to basically search that folder and tell you what is in that folder. And then once that's done, you come back to the terminal. So processes could break their work into different logical parts and create different processes to do those. A little bit of reproduction in the case of processes. You don't need two parents to have a baby process. So a single parent can create a baby process. So a parent can spawn a child by itself. No need for two of them to have fun. So each process has one parent, and it has 0 or more children. And then we usually put processes in groups depending on their parents. Okay, now how do we spawn new processes in Unix? We use this fork system call. This creates a new process for us. So when a process executes fork, it creates a copy of itself with new ID. So this exact same, so the operating system that just gets this memory of this process, it doubles it, and it just gives it another process ID. It says your process ID is a new one. So fork basically creates a new copy of the same process. Now, both parent and child continue the next line after fork. So as I said, both of them are kind of identical copies. So they both start after the fork. So you might say, what's the point of doing this? Now I have two copies doing it. The answer is this fork guy returns a value. So the value return value of fork in the parent is different than the return value of fork in the child. And that's how you can then identify if you're the child or if you're the parent, because both of them have the same code, right? Right after the fork, they're identical. So the way to distinguish between the two is basically by the return value of the fork. Now, if the return value is positive, it means that you're parent and the value is the PID of your child. If the value is 0, it means that you're the child. And if the value is negative, it means that an error happened, so no forking took place. So fork by itself is good. It creates 2 copies, but it's by itself is not perfectly helpful. We might actually not want to run the same code. We want to maybe run a different code in the child. That's where we use this exec. So in the child, once you realize that you're the child, you can then execute exec to start executing a different code. I have an example for this after this slide. The parent process can wait on its children. So once you get the ID, you can say, okay, I want to wait until my child is done. For example, in the example of the terminal that I said, when you put ls, the terminal process calls wait, so it spawns another process, and that another process execs ls, and the parent calls wait. Once the ls process is done, the parent process gets a signal and it gets out of this wait. So that's how it works. And then we have signal. So this basically, you can send signals to processes. For example, you can kill them. So when you kill a process, you're sending it a signal to wrap it up. Your time is over. You're going to die soon. So if there is any last minute things that you want to do it, because you're going to be killed. So it's kind of like a notification that you send to processes. Let's look at an example to make this whole explanation a little bit more understandable, hopefully. So let's say this is the program we have. So initially we have this int PID equals to fork. So this is where we are, let's say. So after we execute this, we'll have 2 copies of this program in 2 processes. So let's say this becomes P1, and then this becomes P0. Now both of them will be here, the next line after fork, right? So there are 2 same copies of the same process. Now they're both the next instruction after fork. Now if this guy is the child, let's say this is the child and this is the parent. So in the child, this PID is 0. So when we check this, we're like, oh yeah, it's 0. So we then come here to exec. In the parent, we check PID, it's not 0. Then we go to else, and we probably want to wait. For example, you don't necessarily need to wait, but you could wait, right? You say wait PID. So I'm going to wait for my child. Now after this, this exec could go and execute a new process, like a new main function, right? So this exec is kind of where we depart from the old process and say, okay, I'm a new process, I'm an independent child, I want to go and see the world by myself and stuff. So that's where you do exec. Okay, So let me see. Can I? Oh, some aside here. With the, I'm going to say this first. Do not do this on university computers, please. So this is a fork bomb, a fun experiment. You can create this one process that repeatedly forks, right? So it just, in a while loop, it calls fork. And what happens is you will exponentially grow the number of children of the first fork bomb. The moment it forks, it creates 2 copies. Those 2 copies, each one create 2 copies, and then each one of them create 2 copies, and so on and so forth. This is kind of like a denial of service attack. So so what happens is, after a while, you consume all the resources that the operating system has. Operating systems can defend against this, so they could just, keep count of the number of processes that are created, and after a while say, no, I'm not going to allow this per user, for example. So each user might have a certain number of processes that they can create. If they reach that, then the operating system is going to say, no, you can't create more. Or it could, limit the rate at which users are creating or spawning processes. Now, as you just saw, we kind of have this parent and children, and then the children could become a parent of another children or a bunch of children, and they could become parents, and so on and so forth. So we basically have a process family tree, and this is specific about Unix. So in Windows, it's a little bit different. In Linux or Unix-like systems, a parent cannot disown a children, cannot say, oh, I don't want my children anymore. So that's not the case in Windows. In Windows, you can pass the children to another process, and another process basically can adopt your process. So adaptation is allowed in Windows. So it's not the case in Unix. In Unix, you can't adopt somebody else's children. Now, the first process that is created in Unix-like systems is called init. Although I have to say this is a little bit old. New systems usually use. Do I have a? Yeah, I think so. New systems actually have. If you look at your process tree, probably you will see SIMD as the initial process. So there is a shift from init to SIMD in recent years. But regardless, systemd or init, there is a single process that is created first, and that process is kind of like grandparents of all processes. It's kind of like the object class in Java, which is the super class of all classes. Now you might ask, who is the parent of init? The parent of init has a PID 0. So init has a PID of 1. So the PID is equal 1. The swapper, the PID is 0 or sketch. And as you can see, this is like kind of the scheduler, if you want to call it. It's kind of like inside the kernel code, and it's really not a process. But anyhow, so usually when we talk about the grandparent of all processes, we're talking about int, which has PID 1. And now this other one, the PID 0 guy, which is again part of the kernel, it's responsible for paging, which is basically the process where, if you don't have enough physical memory, let's say you have a lot of processes, or you have one process that needs more physical memory than you have, you will start to use your secondary storage, your permanent storage, your SSD or your hard disk, to put data there and then bring them back. So this is called paging. And this guy, this PID0, is in charge of doing that. We will talk about this later. In fact, if you go to the schedule, you see that we have demand paging here. That's exactly what we will talk about. Demand. Oh, God damn it. What is wrong? I want to be able to. Are you kidding me? Don't move. This guy is not a good boy. Okay, anyhow, we'll talk about demand paging in the almost to the end of the class. So we'll talk about paging later. So just a pointer for you. We'll come back to this swapper later on. Okay. If somebody's parent dies, so if you create a child and then you die, your child becomes orphaned. But we live in a good society, so somebody is going to come and become the parent of your child, and that somebody is in it. So immediately after a child loses parent, they all go to a very warm home, which is owned by init. So all the orphan processes become the children of the init process. So this is an example. It took me a while to find this one because when you search, PS3, it's amazing because this was in Wikipedia as cited here, but for some reason I wasn't being referred to Wikipedia at the beginning. So I was just searching PS3, and most of the results that would come back had SIMD here, system D. System D instead of init, and because in the slides I was talking about init, I wanted to have init there, so it took me a while, but something like this, right? The init is basically the grandparent of everyone, and then you have a bunch of, so this is the login, for example, process that was created by init. And seems like here whoever logged in, they logged in as a root. So that's why the owner is root, as you can see, of the rest of the processes that are the children of the login. Yeah, you can actually do this PS3 in your system and see what the process tree in your system looks like. I think this is a good time to answer some questions. Okay, so starting from top, do processes created as system boot up have a parent? So there are a bunch of things that the operating system does, and that doesn't, it's not a process. The first process that operating system creates is basically this init guy. But as you can see, this swapper is also here, the one that I mentioned, that is the parent of init. So the first one is the init, right? And the parent of this guy is a swapper. So that's all you need to know. So at boot up, you're doing some stuff. What you're doing is not necessarily in a context of a process, right? You could be just, running some code. You haven't yet created any process. The first one you do is for this init process. And then from there on, you start creating more and more. Do wait have a parameter? I think I explained that. How does it know which processes to wait on? Yeah, I think it was in that example. So if the child process wants to know if it's the child, then we call fork. Oh, the example clears it up. Okay, I'm glad. Why would it be a bad idea to attempt a fork bomb on university computers? Doesn't the OS already have safeguards in place? You can Don't check. Check. Don't check. I didn't say check. Okay? Don't check. But you can. Don't check. What does init do with the abandoned children? The reason you need this parenthood is when the process exits, somebody has to clear things up, and usually that somebody is the parent. So the reason we make init to become the parent of these abandoned children or these orphaned children is because when they terminate, we want somebody to clean things up after them, and init does that. So becoming a parent of child processes, that's pretty much what you're there for. But then you can communicate with your processes. You have some limited control over your processes, that the children. For example, you can kill them, right? A parent process can kill its children, for example, or send them signals because you have their PID, for example. Although you can send signals to other processes as well. But anyhow. Okay, great. How much time do I have left? Not much. Let's see if we can cover some more stuff. Process destruction, normal exit. You compile a code and then your compiler finishes. Good, normal exit. Error exit in a voluntary way. For example, your compiler, you tell your compiler to compile a non-existent file, and the compiler voluntarily exits and tells you, are you kidding me? There was no file, right? It could exit in a fatal, because of a fatal error, and this would be an involuntary exit. For example, your process might have tried to access a memory location that was not allocated to it, and you get a segmentation fault. Or maybe your process attempted to your process might have attempted to divide by 0, and that causes an error, and your process might terminate. Usually when those happen, the operating system detects them, relying usually on hardware to tell the operating system that something like that happened, an error happened. And then in that case, the operating system usually handles that fatal error. In some cases, the process might tell the operating system that I wish to handle this by myself. So if, let's say, a segmentation fault or something like that happens, tell me that and I'll handle that. In those cases, the process has to kind of register themselves with the operating system to say, I will handle those things. I will talk about this. This is where we talk about signals. But if the process fails to handle or wants to ignore something that it should pay attention, like a kill signal, then the operating system just handles it by default. We'll talk about registering signals in a bit later on in these slides. And then finally, you could be killed by another process. That would be also involuntary. So somebody could send a kill signal to you to kill your signal. And you usually want to not be able to kill somebody else's, like one user, like user X shouldn't be able to kill user Y's processes. Usually operating system kind of guards against that. I guess I have to stop here. We're over time. So Next time we'll continue from here. There is one question here. Is it possible to have a chat function in addition to Q&A? It's not my choice. So these live events have only Q&A. They don't have chat, unfortunately, or fortunately. You will never know if I wanted live events or if they forced it on me, maybe. No, but I wanted live events. But anyhow, so sorry, it's not possible to have live chats. If you have questions that you want to interact, go to the website here. Let me show you. Go to the website. Under my name, there is a link, book appointment here. So click on this. Then log in with your stuff. God damn it. Why didn't I log in? Okay. Hello. Why isn't it typing? What is happening? The heck? What is that? Ah, Annie, let me do it differently. Where are we? Okay, so let's do it this way. Share screen, bring Firefox, and send Firefox to these guys. Okay, you see my Firefox now. Good. You go to the course website, SE350, SE. Oh, by the way, go here and rank me high. Be good guys. Like, just say Sayed is the best professor ever. Amazing stuff. Okay, anyhow, SE350. And then you click on here. If you have your stuff, then you can book an appointment with me. So choose a date, choose a time, put your name here, and click book. And then we will meet, and then we can, you know, talk, and that should be good. Okay, so publish. Thank you so much for sticking around and attending the lecture. Thank you for everybody who is going to watch the lectures. Take care, be safe. Talk to you next week. Bye-bye.